Well, by big, I mean big enough to make the statement, okay, that x minus 3 is going to be a big positive number, because if x is big enough, subtracting 3 is not going to change its bigness, okay? And x plus 5 will be a big positive number, and x plus 1 is a big positive number. So f of x is a product of 3 big positive numbers, right? Okay? Which makes it what? What do you get if you multiply a big number by a big number?
A large number.
Yeah, a really big number, right? Now use different words on your homework, right? Okay? Just to try and invoke the idea. And if you multiply that by a big number, what do you get?
Ginormous number.
Yeah, ginormous. Okay, humongous. Okay? Everybody understand that? Because not everybody understands what happens when you multiply numbers, since that's just whatever reads out on your calculator screen when you punch it in. Okay? You have to have a picture of what it means to multiply big numbers. Okay? So that's like 3 big positive numbers. I think you used the word ginormous, didn't you?
Yeah.
It's a ginormous number, positive. Right? What's that mean about your graph? It means as you go to the right, these things are going to go up rapidly. Okay? So we could continue the graph reasonably by doing this. Okay? Okay. Well, if x is a big negative, f of x is a product of 3 big negatives, right? So it's also ginormous. Negative number. What's that do about your graph? It tells you your graph is going to rapidly go down this way. Okay? Even more, when you want to ponder this statement.
It's yours.
I wish I was there.
That's always been part of it.
A large X between, okay, the percent difference between x cubed and x minus 3 times x plus 5 times x plus 1 is insignificant. Okay? So, for example, if I wanted to graph this thing, I don't even need really greatly big numbers. Easily understood big numbers are like negative 100, and 100. Now, if I wanted to graph the x cubed function between negative 100 and 100, well, what's 100 cubed? How many zeros is it going to have? Too many calculators. It's going to be a million. Okay. It's going to have the same shape as your x cubed graph. It's going to look exactly like your x cubed graph, except you're going to have these numbers instead of the numbers that you're used to. So the graph is going to look like this. Okay? And the little wiggles you have in here all occur between, what, negative 5 and 3, right? Where it goes up above and down below and all that. You can't even see that on this scale, can you? I mean, you might be able to see negative 5 because that'd be 1/20th of this. This would be about here, right? Negative 3 or positive 3 would be over about here. So you would have things going on within this interval, but on a scale from negative 1,000,000 to 1,000,000, those little wiggles aren't going to amount to anything that you can see. Okay? So there are little wiggles in here. Little wiggles in here. But they're invisible at this scale. Okay? So if we come back to the graph, if we look over here, it's just going to be much like the graph of the x cubed, isn't it? Doesn't it look like it's going to kind of be that with just a couple little wiggles in here? So we could compare this with the x cubed graph, and it wouldn't be all that much different in its overall behavior. Okay? So the x cubed graph in this region, so if I enlarge this region here and change the scale a little bit, so we're going from like maybe negative 10 to 10 or something like that, and from negative 10 here to 10 here, the graph might actually look something like this. Okay? But if we compress this and then compress this negative 10 to 10 into the scale from negative 1,000,000 to 1,000,000, it's just going to disappear. So we've got this behavior going on close to the origin. We've got this behavior going on far from the origin. Make sense? Okay.